Okay, well, no, I used my fingers to try and move it, and I couldn't. I just had to go by it until it got too complex to get all the way through. Where I had to try and move it on my fingernails, so it was grab it with
Was you just like 6 minutes?
No, it just felt like there was something lost in my eye, so I had to get it out.
But you knew it wasn't there. How did you just feel like today?
Well, I've known it had been there for 2 weeks.
And you didn't do anything about
Well, I couldn't find it for the 2 weeks.
it? Just magic.
Yeah,
Hey, look, it's okay. As long as you got that out of your way now. Like, legit audibility.
I would explain the headache I got, and then from there,
Oh my god. That's scary.
yeah.
Oh,
I don't know if it was my dog that I have personally, or if it's my bed dogs, because I found it when I was going through my stuff in 6th grade.
So you're saying that since 6th grade?
All right, questions that you have before we get going today, ladies and gentlemen.
So limiting reactions is just determining what runs out in your equation?
Yes.
Okay.
Yes,
That's
That
cool.
sounds.
it is.
It's interesting.
Because all you're doing is the same thing you have been doing, but now you need to do it for both reactants. Now, again, I can only give you information 3 ways. I could give you the grams of a substance, converted into moles. I can give you the volume of a gas, PV equals nRT, to convert it into moles. I can give you the molarity and the volume of a solution. Where people are struggling is realizing that molarity and volume are of a solution, and then you cannot take that same volume and plug it into a gas law, because it is the volume of a liquid. It is not the volume of a gas. Now, those are the 3 ways that I can give you information. When you are done, the 3 ways I will ask you to report out your answer are: tell me how many grams of something was produced, tell me what volume of gas was produced under certain conditions, or tell me what the molarity of the solution was at the end. That's it. Okay? And there are 3 steps to doing the problem after you write a balanced equation. Take what you're given, get it into moles. 2, molar ratio step. Molar ratio allows you to go from one part of the equation to another. And 3, report out in your final answer. That's it. That's the entire thing. Now, what is killing you right now is some of you are taking 25 minutes to write a formula, and then you have no time to do the problem afterwards. Your quiz on Friday, 1 question, 13 points. 1 problem. Okay? Now, again, I haven't written your test yet, but in the past, the test has been a 6-question test, 6 problems, used to be done in 51 minutes. Okay? I haven't decided how many I'm giving you yet. By the way, in those 6 problems, it was worth about 120 some points. So I'll show you how I start grading today. Okay, here's where we left off. Okay, so again, first thing you have to do is write a balanced formula. Ammonium is one of the most common products produced in the United States. It is used to make fertilizer and other products. Ammonium is produced in a synthesis reaction, meaning there is only one product, between nitrogen gas, N2, and hydrogen gas, H2. Now, there are 2 of these, there are 3 over here. I don't care about that. I will take care of that when I balance. I have to write a good formula here. The formula for ammonium is NH3. The formula for hydrogen is H2. I don't care that there's 2 here and 3 here. I can take care of that when I balance it. N2, why? Nitrogen and hydrogen are both diatomics. Questions? Take what you're given, again, I took the 1.50 times 10 to the third grams of nitrogen. I got it out of scientific notation. That gives me 1,500 grams. I take what I'm given and I convert it into moles. Now, these problems, to keep them straight, my suggestion is you tell me grams of what substance so that you know which one you're working with. Because you're going to have the same 1,500 grams, but you're going to have it of hydrogen gas. We take and we convert it into moles. How do we get from grams to moles? We use formula mass. 1 mole over the formula mass, 1 mole of nitrogen over 28.02 grams. Why 28.02? Each hydrogen is 14.01 times 2 is 28.02. I'm then going to take it times the molar ratio. Now for your molar ratio, ladies and gentlemen, it is the moles of what you are going to, NH3, compared to the moles of what you are given, N. The moles of what you are given always have to go on the bottom because it is the only way they will cancel out. If you haven't noticed, that's why we call it the unit cancellation method. I'm setting it up so that my units cancel out, so that I move from one unit to another until I eventually get to the unit that I want. Grams of nitrogen are canceling here. Moles of nitrogen are canceling here. I'm now in moles of ammonia. Okay? 107 moles of ammonia. Now, I'm stopping here. Why? Why don't I go to grams? Well, here's the thing. In these problems, it is not a big deal for me to put in one more step and go to grams. And I could do it with both of these. But if I'm going to PV equals nRT, if I'm going to find the molarity, I don't want to do extra work for something that I don't have to do. So I stop after the molar ratio. After the molar ratio, not before. Because I want to compare how much product I can make from this reactant and how much product I can make with this reactant. Because this ratio step will determine how much I can make. And even though I might have more of one than the other, the one that there is more of doesn't necessarily mean that that's going to make the most product. Okay? The one that there is the most of doesn't necessarily mean that's going to make the most product. The only way I can do is to do this calculation and figure this out. Same amount of hydrogen gas. 1 mole of hydrogen gas over 2.02 grams. Why 2.02? Well, because it's hydrogen gas. Hydrogen gas has a mass of 1.01 for each hydrogen. There are 2 of them here. So I make that 2.02 for hydrogen. There's a typo in this next step that I will fix right now, ladies and gentlemen. Okay? I will fix it right now, but it is still the ratio step. The typo is because I'm a huge fan of cutting and pasting. So in here, it should have been hydrogen gas on the bottom. It should not have been nitrogen gas because... Sorry. Okay. Oops. Okay. So, taking the grams, getting into moles. Taking the moles, using the molar ratio. Now, the molar ratio here is 2 to 3. The molar ratio here was 2 to 1. So this molar ratio actually increases the amount of ammonium based on the amount of nitrogen gas. This one here, it takes 3 moles of hydrogen gas to make 2 of ammonia. That is a very different ratio than here. But because we have 1,500 grams and because the formula mass is so much smaller here, we get a lot more moles of this. So even though we're taking it times 2 over 3, it still comes out to be the larger amount. Now you can only make one of these 2 amounts. And the amount that you can make is always the smaller amount. Always. That is it. In other words, when I make 107 moles of ammonia, I'm going to have some of this left over. I'm going to have 387 moles that I could make for ammonia with this, but I can't because I'm out of the nitrogen. You can only ever make the smaller amount. Now, the actual limiting reactant is therefore nitrogen gas. It is the one that we run out of. That is your limiting reactant. You will have to identify that on a test. This is the one I run out of. You can do it by putting LR by this. You can go back and circle this and put an LR by it, meaning that's the limiting reactant. But you've got to know which one you create. Okay? This is where we left off yesterday. Questions? Now that I know which amount I can make, I'm going to finish the problem. So now I take that 107 moles that I can create, and I want to get it into my final unit, which is grams of ammonia. So I'm going to do grams of ammonia over 1 mole of ammonia. Taking what I have created, the amount of it, putting it into its final unit. Now you'll notice here, moles was on top, grams was on the bottom. Why? Going from grams to moles. Here I'm in moles, so grams are on top and moles are on the bottom, because I'm going into grams. And I can make 1,820 grams of ammonia, according to this reaction. Questions? Just so you know, if you decided to put this step in here and in here, this is still going to be the limiting one. This is still going to be the limiting one. Okay? This one would be about 5 times greater than this, a little less than 5 times. So that would mean we would be looking at around 10,000 grams. That we would be looking at. About 10,000. Oh, no. Oh, no. Who do you want?
Hi, everyone.
Who do you
Viewers
want?
are all welcome to the Career Center. So Mr. Brand can get a break.
Go, follow her. Go, everybody. Can't believe he went.
Wait. Wait, not supposed to. Wait, I'm sorry. Wait.
Questions, ladies and gentlemen.
I thought you was being for real. I'm sorry.
You guys all saw her, right? She was for real, correct?
Yeah. No, and then she said she was kidding. I got so excited.
Not near as excited as I did thinking you were leaving. Questions?
How do I get out of scientific notation?
What do you mean, how do you get out of scientific notation?
In my calculator.
Into your calculator. Book into your calculator.
DRG, and then, oh, it's just degree. Oh.
Stop doing all because I'm not.
Thank you.
Okay. If 212 milliliters of 0.425 molar magnesium sulfide is mixed with 194 milliliters of 2.99 molar aluminum chlorate, how many grams of precipitate would form? No, actually, this is very typical to what's going to be on your test.
Is it?
Yeah. Okay. So what's the first thing we have to do?
Balanced equation. No, I read it formula.
Okay. So we are going to begin with magnesium sulfide. Magnesium is a +2, sulfur is a -2, therefore MgS. And it is aqueous. How do I know it's aqueous? Because it's given me a molarity. The only way you can have a molarity is if it's a solution. Aluminum chlorate. Aluminum +3, chlorate -1, AlClO3. Aqueous. Why? Got a molarity. Now, it wants you to figure out how many grams of what? Precipitate. Okay. You need this side of your solubility chart. What kind of reaction is this? Come on. Double replacement. Two couples go to the dance together. Halfway through the dance, they decide it's not working out, so they switch partners. By the way, chemistry world is homophobic. A guy has to change places with a guy. A metal has to change place with another metal. You will not end up with a compound with two metals and two nonmetals together. So magnesium and aluminum change places. Magnesium does not change its charge, though. It is still a +2. Chlorate is still a -1. So therefore, MgClO3 in parentheses with a 2 by it. Aluminum is still a +3. Sulfur is still a -2. So Al2S3. Now, when you look up chlorate on on this table, ladies and gentlemen, nothing precipitates with it. Nothing. That's why chlorate is often in these problems, because you know what? You can put it with whatever you want, and it won't precipitate right away. Then at the end, you put what it was with something else that precipitates. When you look up sulfur down here, ladies and gentlemen, at the very bottom, top of the bottom table, sulfur says that it will precipitate with most cations. Excuse me. Exceptions being ammonium or cations in group 1 and 2. Here is group 1 and 2, ladies and gentlemen. Aluminum is not in there. Aluminum is in group 13. Therefore, it precipitates. It makes the solid. You would be amazed how many times people do the problem absolutely perfectly correct, and they tell me how many grams of this were produced and I have to mark it wrong because that wasn't the precipitate. Now I'm going to make a note for myself, ladies and gentlemen. 212 milliliters of 4.25 molar magnesium sulfide, 194 milliliters of 2.99 molar aluminum chlorate, and I'm trying to figure out how many grams of this. Gonna have to do the same exact calculation twice. So we begin with this one. You can begin with the other one if you want. I don't care. I'm going to take my 212 milliliters. I'm going to convert it into liters. Why? Because then I can use molarity to get out of liters and into moles. This is this, written the way that is more useful to you. Because 4.25 molar means 4.25 moles in 1 liter of solution. The problem is I don't have 1 liter. I only have part of it. So guess what? That means I'm only getting part of these moles. Volume times moles over volume, going to give me moles of magnesium sulfide. What's the next step? Molar ratio. Take what you're given, get it into moles, use the molar ratio. I would write those down if you can't remember on your periodic table. Step 1, convert to moles. Step 2, molar ratio. Step 3, report out in your final answer. That's it. That is the entirety of these problems. Now I need the ratio. Your ratio is always what you are going to on top, aluminum sulfide. What you are in on the bottom, 3 moles of magnesium sulfide. 1 mole of aluminum sulfide over 3 moles of magnesium sulfide. I am going to stop there. Figure out how many moles. Questions? Now, I'm going to do the exact same thing for the aluminum chlorate. Here we have the 194 milliliters put into liters. By the way, you'll notice, what didn't I calculate for MGS? Never calculated a formula mass. Why? I didn't need it. I wasn't given the grams of it. I was given the molarity. I was given a volume. I don't need to calculate the formula mass. Okay? Don't need to calculate the formula mass. Take this times the molarity. 2.99 moles of aluminum chloride over 1 liter of chlorate, not chloride, chlorate. Then my ratio. You'll notice the top of this is the same. Why? Because we're going to the same substance. The only thing that changes is the bottom part. Do the math. There you go. Now these are pretty darn what? Yes, go ahead,
Is that
Joseph.
supposed to be aluminum chloride?
No, it is not. It is the moles of product. We have to get to moles of product. Great question. But this ratio step here, Josie, I need to compare moles of product to moles of product. How much product does each one of these create? What do you notice about these two numbers? They're very close. Matter of fact, it wouldn't surprise me on a test if some mean teacher gave you a problem where if you rounded too much, you might not find the right limiting reactant. So don't be rounding these. Carry at least 3 or 4 sig figs. The difference might be in the 3rd or 4th sig fig. Which one of these can we actually make? Which one is our limiting reactant? What? The bottom one. What is the substance that is the limiting reactant? Thank you. AlClO3. You are correct. We can only make the smaller amount, which is the bottom one. But the actual limiting reactant is here. Questions? Okay. What do we need to do to finish? Because we're not done.
Put it into grams.
Put it into grams. Take that smaller amount of moles and put it into grams. Now I do need a formula mass, but it's a formula mass of aluminum sulfide. 2 aluminums, 3 sulfurs, 150.17. 1 mole. There is your answer, ladies and gentlemen. There is your answer. Questions? Okay. If I were grading this, ladies and gentlemen, by the way, I'm not going to give you a limiting reactant problem on your quiz on Friday. You'll only be one of these. But if I were grading this, this would be 2 points. 1 for the number, 1 for unit and sig figs. This conversion is 2 points. Getting or using the correct number here is a point. 2 points for writing the correct formulas on each side. 1 point for balancing it correctly. This times this is a point. A point here because you converted correctly from milliliters into liters. Using this correctly, correct ratio, getting this answer correct. Converting that to liters correctly, using the molarity, correct ratio, correct answer. So let's do a little totaling here.
Is identifying if it's a limited reactant.
Oh, thank you. 2 points for identifying the limiting reactant. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20-point problem.
And it's only going to be 1 problem?
Slow down.
Okay.
On your quiz, I will not give you the limiting reactant part. That's why it's only 13 points.
This Friday quiz.
This Friday quiz.
No,
Next Thursday test. Yeah, all of this.
Ooh,
Thank you.
excellent.
Questions? And multiple problems like this
On the test.
on the test.
How do you know if it's a limited reaction problem?
Because I will give you information about both reactants.
Oh, okay.
If I tell you something is in excess, it means whatever is not in excess is the limiting reactant. So like in the problems I've been giving you, I've only been telling you about one of these two things. Then it's not a limiting reactant problem. That is the limiting reactant.
Will it be?
Now what we've done is we're saying, okay, if you can do these, well, now I can give you a limiting reactant problem because you're just doing the same thing twice. Okay? You're figuring out how many moles of product you would create. But again, Josie, be careful. We got to get through the ratio step to compare moles of product. You cannot compare moles of reactant to other moles of reactant because the ratio may make them change how much they can make.
The numbers in front of the mole, in the molar ratio, that's just based off the balance, right?
Correct.
Okay.
And that's what gives us this. So what this is saying is 3 moles of this compound, magnesium sulfide, react with 2 moles of aluminum chlorate to produce 3 moles of magnesium chlorate and 1 mole of aluminum sulfide.
Okay.
So the numbers that are up there are actually a molar ratio. Just like within this formula, there is a ratio of 1 mole of magnesium to 1 mole of sulfur. That's a molar ratio. So earlier we were doing molar ratios within a compound. Now we can do them within an equation. That is why whenever you are confused, take what you're given and get it into
Mole.
moles.
So the problems we did yesterday and the day before, the molar ratio was from inside the.
The molar ratio is always from your balanced chemical equation.
Okay.
Always.
Always the number in front?
Always the coefficients in front.
Okay.
Always. Always. That is why it's important that you balance them and balance them correctly. Because otherwise you will not get the correct formulas here.
Okay.
Good. Other questions? Okay. So 50 milliliters of 2.11 molar sodium iodide reacts with 25 milliliters of 2.25 molar lead-2 nitrate. How many grams of precipitate are produced? This is exactly what you're going to do in the lab tomorrow. The only difference between this problem and your lab tomorrow is the volumes and the molarities will be different. You are going to take sodium iodide. You are going to mix it with lead-2 nitrate. Sodium iodide, Na plus 1, I minus 1. It's going to be aqueous. Lead-2 nitrate, Pb plus 2, nitrate minus 1, Pb NO3 in parentheses 2. Nitrate is one of those things too that will not precipitate with anything. So the nice part about using it in a reaction is whatever it's with at the start will not precipitate. Lead precipitates with a lot of things, ladies and gentlemen. A lot of things. So that's why we put it with nitrate at the beginning. When we get this double replacement reaction and sodium and lead switch spots. Now, by the way, I don't care which one of these you write first on the product side. That doesn't matter. The two products are these things. I don't care what order you put them in. The same way, these are the two reactants. I don't care what order you put them in. It doesn't matter. As long as they're on the correct sides. Okay? Questions? So, sodium nitrate. Sodium plus 1, nitrate minus 1. Charges cancel out. Lead-2 iodide plus 2 minus 1. Why lead-2? Because it was a 2 over here. It's not going to change charges. So PbI2. When you look at your table here, ladies and gentlemen, again, nitrate, nothing precipitates with it. Nothing. Iodine, there are a few limiting things that will precipitate with it. Silver, lead, and mercury. It's with lead. That's your precipitate. You are going to make this in the lab tomorrow. Okay? You're going to make it. Now, what are we given? 50 milliliters, 2.11 molar. 25 milliliters, 2.25 molar. We're asked to figure out how much of this you're going to produce. That is exactly what you're going to do in the lab tomorrow. Before you ever begin the experiment, you will know how much of this you are supposed to get, because that is what this calculation is. This calculation tells me, here's how much stuff I should make. Now, I don't guarantee in your experiment that you will do it correctly and get that exact amount. But we're going to find out how close you come to it. So I'm going to take the 50 milliliters, 50 milliliters, 0.050 liters. Why? The only way I can use this with molarity is if they are both in liters. Took the molarity and wrote it out as 2.11 moles of sodium iodide over 1 liter. Liters and liters cancel. The ratio step, I'm going to this. 1 mole of this, 2 moles of this. That is how many moles of lead iodide I should produce from this volume and this molarity. Second calculation, different volume, 25 milliliters or 0.025 liters. Different molarity, 2.25 moles of PbNO3 over 1 liter. And a different ratio, 1 mole of PBI for every 1 mole of PbNO3. 1 and 1. Questions? Which one of these two amounts can I create?
The top one.
So what's the limiting reactant? NaI. In your lab tomorrow, some of you are going to have a smaller amount of one of these than others. We will all use the exact same amount of this. One group will use 5 milliliters of this. The next group will use 10. The next group will use 15. The next group will use 20. The next group will use 25. And the next group will use 30. Why? Each one of you may have a different limiting reactant then. We're going to figure out which one's the limiting reactant in every one of our trials. Okay? We've done that here. Smaller amount means that's our limiting reactant. But again, we are not done. Why?
Because we have to put it into grams.
We have to put it into grams. So now we take that smaller amount. Lead iodide is 461 grams for lead iodide per 1 mole. We get 24.3117 grams of lead iodide. Sig figs, 24.3. Now, here's the problem that you're going to have tomorrow. These two reactants are both what?
Pretty close to
Solid, liquid, gases, solutions. Please, don't everyone jump on it all at once. Even though you've got a molarity, don't let that help you understand what their solution. Which means you're going to make those grams of precipitate into what? So think about this. You take this liquid and this liquid solutions and mix them together. A precipitate is a solid that does what? Settles out of solution. But it's still where? In the solution. The only way to get the grams of it is to get it of the solution. So you're going to spend time tomorrow with your good friend filter paper. Filtering it
like
to get the solution part away from the solid part.
What if we mess it up?
What is
Then
the
your
actual,
results
like-
are going to be terrible and you'll be penalized for it.
Are you gonna tell us the actual process of the lab now, or just tomorrow?
Tomorrow.
Okay.
We got time.
Well,
Let's not.
are we putting liquids into liquids? Are we Bunsen burner?
Whoa. Did you honestly just ask that question? After we just said both of these things.
Okay, so I'm guessing we're gonna take two things. Mix it on this and do the thing, and I'm gonna filter it. Okay.
Whew, you are on top of it.
I'm sure.
Questions?
It's like making ramen. It's like making
Oh,
ramen.
everything.
No.
Out of the water. And then sprinkle in your seasoning. Mix it. Last time I had ramen, I was.
Okay. 65.3 milliliters of 1.25. By the way, sorry, should be molar.
It says mass to volume on the bottom. Does that make a difference?
It says molarity and mass to volume limiting reactant.
Yeah, but the other one's gonna say volume.
You have to find a mellow.
That's because there was no volume involved because there was no gas involved.
So is there a gas involved now?
Well, let me finish reading the question and maybe we'll find that out. 65.3 milliliters of 0.125. By the way, that should say molar.
It's PB and RT, so you give it a temperature pressure.
What? We're going to do PV equals nRT because I'm giving you a pressure and a temperature? My gosh, it's about time you started paying attention. 65.3 milliliters of 1.25 molar phosphoric acid reacts with 7.56 grams of strontium metal. How many milliliters of hydrogen gas are produced at 70 or 97.6 kPa and 28.6 degrees Celsius? You know what I love about this question, ladies and gentlemen?
It's complexity.
It has everything in it.
Yep.
If you can do this, you should be able to do any problem I give you. Because it has molarity, it has mass, and it has gas law. All three are in here. All three are in here.
That's cool.
Now again, if you can't write phosphoric acid and get H3PO4, you're probably not going to get the problem right. If you don't know that strontium metal is SR with an M after it, not a 2 after it, just SR, probably not getting things right. Hydrogen and strontium switch places. Why? It's a single replacement reaction. Giving us strontium phosphate. Strontium is a +2. Phosphate is a -3. That means SR3. PO4, 2. Hydrogen gas is a diatomic. You don't put the 2 there, guess what? It's not going to balance correctly. We balance the equation. 6 hydrogens here, 6 hydrogens here. 3 strontiums, 3 strontiums. 2 phosphates, 2 phosphates. Questions? Again, little step goes a long way. 65.3 milliliters of 0.125 of this stuff. Why do I do that? I don't want to have to go figure it out reading the problem 2 or 3 times. 7.56 grams here. How many milliliters? Notice it says milliliters. At 97.6 kPa, 28.6 degrees Celsius. Take what you're given, do what? Here's my milliliters, convert them into liters, times the molarity, times the ratio. Ratio of what I'm going to, 3 moles of hydrogen gas. Ratio of what I'm in, 2 moles of phosphoric acid. 0.012243 moles of hydrogen gas. Got to get the product. Take what I'm given. 7.56 grams of strontium. Get it in 2 moles. Formula mass. 1 mole of strontium, 87.62 grams of strontium. Ratio, same 3 moles of hydrogen gas on the top. Different amount of moles on the bottom. Why? Because this is a 3-to-3 ratio. That's how many moles of hydrogen gas I could produce. Which one of those can I make? Top or bottom? Can only do the smaller amount. That's the one on top, ladies and gentlemen. That is the one on top. So how do I get that from moles of hydrogen gas into a volume of hydrogen gas? PV equals nRT. PV equals nRT. You get a point for selecting the correct R value. You get a point for converting temperature into Kelvin. Then you just got to do the math here. Solve for V. V ends up being 0.31439 liters. 314 milliliters. So 2, 4, 5, 6, 7, 8, 9, 10, 11, 2 points here. 12, 13, 14, 15, 16, 17, 18, 19, 20. 20-point problem. And that's everything. That's all. Questions? Limiting reactions. Chemistry Unit 7 worksheet. Go to work.
Did you get hungry? Whoa. Don't say that.
You got hungry.
Yes. What's that? Definitely. The staples are even free. Take as many of them as you'd like.